So I want to make a start on IR generation today. So I'm going to generate a linear intermediate representation that looks a bit like assembly. But before I do that, I need to clean up a couple of bits that I've been meaning to fix. So the first thing is in the parser. The parse expression error I changed to include return. That's actually not correct because return can't start an expression, so I'll just change that back. Second thing is that in the type cache for functions, I forgot to initialize the key with the offset. So the key is an FNV1A hash, but I need to initialize it with this offset before I do the actual loop. And then the next thing is that in the checker, when I propagate a type, when I get to binary nodes, I set the type, but I never propagate down those subtrees as well. So I need to call tc.propagate on here. And then when I call that, that will set the type anyway. So with those fixes out of the way, I think I'll start generating some IR. So we'll have ir.go. I'll just put everything in here so I can figure out what I actually need. So we want to have a new generator. And the generator is going to generate functions. So it's basically going to work on a module at a time, where I'm calling a module a file, basically. So we'll have, for example, in a file, we're going to basically generate IR for individual functions. So we'll keep a list of functions. So we'll say functions here. So we'll need a function type. And a function will have a name. It will have params, which we'll need to store for generating machine code with the correct calling convention and everything when we get to actual machine code. The params are just going to be, I think these will be a slice of something called a value, and returns will be just a type. And a type will basically just be an enum in this case. A function will also need a list of basic blocks, and we'll keep track of the entry block. So I just need to create, I'll do value first. So a value will be something that can be used as a destination or a source operand in an instruction. So we'll need some kind of a like value kind. So this will be, for example, is it an immediate or is it a register or something like that, or like a global or something. And initially what I'll need is that I only have integers. So if, for example, this is an immediate, then the value will be, say, a converted int64. What else will I need? I'll need the type of the value. So I'll store the value in an int64, but it could just be like a signed 8-bit integer. So we'll need a type here as well. And the IR package will have its own types that it will convert from the main language types, because the main language types won't make much sense as we lower it down into actual machine code. So we've got a kind, a value, a type, and I think we'll also take an ID. So for example, if we're creating registers, if this represents a register, it will need a register ID, basically. And maybe I could just reuse value for that. I think I'll reuse value for that for now. So we'll need some way to generate IDs. So we'll say, or I suppose registers. So we'll say reg ID maybe can be an atomic int64 because we'll populate value with the reg ID. We'll also need value kinds. So we'll have type value kind. This can just be an int for now. And we'll create a few kinds. So we'll have, we'll say we'll have invalid just so that the 0 value is something that shouldn't be used at the moment. Then we'll have immediates and we'll have registers. Then it would be useful to have types next, I think. So we'll do type will also be an int. And this can, we basically want to map fin types into IR types. And right now I only have integers, so they're all going to be basically the same thing. But we'll do this anyway. So we'll have void. Void will be the 0 value for something that doesn't, there is no real type around it. We don't know what to do with it. So for example, if a function returns nothing, then the type will be void. So in this case, that will be iota. And then we'll have SA, S16, S32, and S64. And we'll want some way to create a new type. So we'll do function new type. We'll return a type. And we'll create new types from the types dot type. So we'll do a switch on here to say, okay, we'll switch on the type. We'll do a type switch here. So we'll say that in the case that we've got types.basic, then we'll return a basic kind type, and we'll index into that using type.kind. So here we'll have basic kind types. And this can map to the type. So for example, we can have types dot S8 maps to S8. And the same for all of these actually. So I'll just copy these in here. I'll move this type stuff out into its own file. So we'll say types.go. That can go into there. Value kind, I think I'll also move this into its own file as well. And we'll want a way to create different kinds of values. So for example, we'll say new register. In this case, we will take the type that the register should be. So this will be one of the IR types that we pass in, and we'll return a pointer to a value. And the way that we'll initialize this is to say that the kind is reg. The value is regid.add1, and the type is whatever type was passed in. We'll also need a way to create new immediates. So we'll do new immediate here. Immediate can take a value because this will be, for example, an integer literal or something like that. And so this will be basically the same thing, but the value will now be the value that gets passed in, and its kind will be immediate. So those are the only two values we have right now. And it might be useful to implement the stringer interface as well. So we'll say pointer to value string, return string, and we'll do a switch in here based on the v.kind. So in the case that it's an immediate, we'll just return the strconv.format int, and we'll pass in v.value, and I think it takes in the radix. Let's see, go doc strconv.format int. The base. So base 10 int 64. So I don't need to do any conversions there. We'll just return this just as it is. And then in the case of reg, we'll return be the same thing, but we're just going to prefix it with v. So if something is prefixed with a v, we'll just say that it's a virtual register. And then we'll have some default panic, just in case we add another one and forget to write the stringer for it. So we'll say format.sprintf unhandled value kind, and we'll put the value kind. I think we'll just do v.kind. Maybe on value kind we'll also do the stringer. So we'll say v value kind string return value kind names by v, and then we'll do up here we'll say value kind names. So this is going to be invalid maps to invalid, immediate maps to immediate, and reg maps to reg. This needs to be string here. So that's values, and we'll use values and instructions and stuff. So back to the IR. We have functions. We've implemented the type for values type block. So block is going to be another struct. Blocks can have labels, and they can have slices of instructions. So let's say insta maybe. And an instruction will be just one line of IR, assembly like IR. So the instructions are going to have an operation that they're going to do. So we'll have some op kind here. They're going to have some list of destinations, which will be values. And they'll also have sources, which will be values as well. So I think that should be enough to get started. There are a couple of small changes. So for example, let's see, we're using somewhere in here, it might be the types one actually. We're using type.kind. This isn't actually public, so I need to change this to be public here. Change it there. It's probably used in the cache as well, so I should change it down here. And while I'm here, I may as well also change the function, because I'm going to need access to these params and returns as well. So let's just go test and see where these are actually being used. So cache, I need to change line 92. Okay, these ones need to be uppercased now. And then in the actual function thing, we need to say f.params is now uppercase, and the same thing with f.returns. Okay, so undefined basic kind types. This needs an S. Missing a return on line 27. Yep, so in this case I'm going to do another panic. So we'll say panic fimp.sprint f unhandled unhandled type t. We'll just pass in type. And then we need opkind, so let's get back to IR over here. So we'll have some type opkind. This will just be an int again, and we'll define a bunch of them up here. So we'll say invalid op can be 0. So this one can be opkind equals iota. Then we'll have I'll need a few different ones. So I need a way to load immediate or constant values into registers. So we'll call that one const. We'll need a way to return. So we'll have return. And we'll need a way to do arithmetic as well. So we'll have add, sub, mul, and div. I think these should do for now. And we'll need to be able to print these out to debug. So we'll say func o opkind string, return opkind names indexed by o. So this will be var opkind names equals ... to string, and we'll just copy all of these in here. Okay, now before I go too much further, I think we should add a stringer to each of these types as well. So an instruction needs to be able to print itself as like a 3 address code sort of thing. It's not strictly 3 address code because there are multiple destinations and there could be more than 2 sources, but for the most part it's going to be 3 address code. So we're always going to start with building up the destinations and the sources. So we'll just say DSTs is a slice of strings. So we'll loop over each DST in i.dsts. And then we'll just append the string here. So maybe what I'll do is for destination, I want to attach a type to it for the output if there is one. So we'll say that string equals dst.string. Then we'll say if type equals let's see, we've got dst dot type.string. So if that is not equal to empty string, we'll add it on. We'll do that with a colon, space, and then the type. Then we'll append that to destinations. Sources, I don't want to attach types like that because I should be able to look up the type if needed. If I decided to read this in as another actual language, then I could just look up the types from where they've been defined before. So sources is going to be from sources, and we're going to get source on here, and then we'll just append the source.string in this case. So what we'll do is we'll say that if the length of destinations is nothing, then we'll just return fimp.sprint f, and we're going to say just the op followed by all of the sources. So we'll say i.op followed by strings.join i.sources which will join together, or not i.sources, this will just be sources, which will join together with a comma space. Otherwise we're going to do exactly the same thing, but we're also going to include destinations. and destinations will go on the left side of everything with an equals. So then to stringify a block, or to print a block or whatever, we'll say block string. So a block, if it's got a label, so we'll say, let's just do string. We'll say if b.name or b.label does not equal nothing, then string is going to start with the label followed by a colon. Then we just need to build up all of the instructions. So we basically just need to do insters is string, and then we'll do a for over each inster range over b dot insters. And here we're just going to append again. So we're going to say append this to this, and we'll say inster.string, return the strings.join of insters by a new line. So each instruction will go on a brand new line. Then we've got function down here. So to stringify a function, we will start with fn space plus the function name, which should always exist, plus some parameters, some returns, and then the body, which will just be all of the instructions from the blocks. So I think in this case we're only going to start off with one basic block anyway, so I'll just keep it simple with just I'll just put the entry block in, maybe. Or actually, I'll loop over all these, but I'll just I won't bother putting the entry block first at the moment. So at this point, we need to do for block range over f.blocks. Here, then, we're going to say that string plus equals strings dot, we want to split the block dot string by the new line, because I want to indent it. So strings dot join, we'll join that by a new line followed by a tab, and then we'll make sure that it is preceded by a tab as well. So that's each block there, and a new line, I suppose. Maybe we'll leave the new line off of there, and we'll just put the new line here and at the end. And then we'll just return that string. So the other thing that I think I need is that I want to group all of these functions into a module. So the generator should return a module. So we'll say that a module is a struct that just has some functions in it at the moment. So functions is going to be this function slice, basically. And the way that we stringify a module is by saying module string. We'll have functions is a load of strings, loop over each function, and then just append. So this will be fn.string, and then we'll return the strings.join of fn's with two new lines between them. So generator, we need a new generator constructor. This will return a new generator. Then the generator needs a generate function, and this will return a module and any errors. So we're going to need to keep errors on here, although I won't fill out any errors to begin with. But we'll go to the checker, to the check function, and just take this code for actually making an error, if there was one. So this is G errors, and we'll take the error helper just so we've got it. Then if I want to generate an error, I can. So I think we're going to be working on AST nodes, so it makes sense to still take this AST node in. And I think it can basically stay the same. We'll just change TC to G. So this also means that a generator needs to take in a file. And these things need to be reset. So if I go to check, and we'll just see, yeah, so these things just need to be reset when we call generate. And instead of TC, this is going to be G, and I need to also take this error lines. I think I just need to keep it in the struct up here. So this can go down here. Okay. Then if everything went okay, we'll basically return a new module where functions is set to be g.functions. So when we come into this function, we should also reset the function slice as well. And then I can just, let's see, we've got mod can equal this, and we'll return mod and nil. Maybe we'll do it this way. Okay. So after I've reset the internal state, I need to call g.generate on some node. So we're going to pass in an AST node, and we're going to pass in a file. So this will be token.file. And we need some generate function that knows how to walk the tree. So this one won't return anything. Or generate should return a slice of values that could be used as either destinations or sources in further up the tree. So we'll return slice of value. This only needs to accept a node because file is part of the internal state. So we'll do a switch on node type. First thing, like usual, is to have a default panic. Fimp.sprint f unhandled type t. That would be node. Okay, so the first thing is the module. So we're going to be passing in a module as the first thing. So this is for each decal range over the node.decals. In this case, we want to call g.generate on the decal. And this will be the same for block statements. But this will work on statements. The next thing, so we've got to return something as well. So we'll return nil from here since these don't produce any values themselves. Then when we are going into a module, we're going to be hitting a bunch of function decals. So to generate a function declaration, the function declaration itself won't return any values, but we need to call g.generate on the node body. And we'll need a place to keep instructions as we go through this tree. So I'll keep a block here, I think. We'll just say that we've got a block for now. I'm also going to lowercase this because we don't need access to it anyway from the outside. So we'll have a block, and this block can be appended to the function block when we've finished using it. So we'll say, for example, that we've got fn is a new function where the name is node.name. We'll also have to set up params, which we'll create in a minute, and we'll do returns. Then what we've got is, so we've got name params, returns, blocks, and entry. So blocks and entry, I think I'll leave those for the moment. So we'll say g.block is equal to a new block, and we won't bother adding a label just yet. We'll just initialize it. And then at the end, we'll just say that function.entry equals g.block, and we'll also make sure to push this or append it onto the slice. Okay, so we've got the blocks and the entry. So we'll have the function declaration. We'll initialize some internal state to keep track of instructions in this block. So that means that in the block statement, we're going to be generating for each statement. Then we can do stuff, for example, like saying the return statement. So the return statement's where we're going to have our first actual sort of instructions being generated. And in this case, so we'd want to say, for example, g.block.instars append to this. Maybe so I don't have to keep on typing this out, I will have an emit helper. So let's go to block. Let's make a new function here called emit, and this will be an instruction. So the instruction will just be pointer to instruction, and its only purpose is to do b.instars equals append b.instars instar. Instruction. Okay. This will just help me to not type out append every single time I want to generate an instruction. So we're going to emit an instruction. So we can say ampersand instar, and then just emit instructions like this into a block. So g.block.emit. So an instruction needs an op. Oh. It needs an op, it needs some destinations, and it needs some sources. So in this case with return statement, we don't have any destinations, it's only sources. And the sources are the expressions. So we'll say sources is a bunch of values. And the values are going to be expressions. So we've got expression for range in the node expressions. And we need to generate, the op as well is going to be return, and this will be sources is going to be sources. So for each expression in the return statement, we need to generate we'll basically be getting some values back from a call to generate, where we pass in the expression. And then sources equals append sources, and we'll just spread those values into this slice. In most cases, it's just going to be a single value that's being appended, but in some cases, we'll end up with multiple returns and things like that. So that's return statement. We're going to need integer because that's the only actual value we can use right now. So in the case of int, we actually want to load the integer into as like a constant value into a register. So we need to create some destination, and the destinations is going to be a slice of value where we say that we want a new register, and the type of this, so if I go to values, so new register just needs an IR type. So the IR type, we already know we can look up the type from the types package because we've attached a type to the AST node. So we'll say new type, and then we'll look up types.nodeType, passing in the node. So this should return, for example, S32 as an IR type instead, and we'll create a new register based on that. And the source is going to be the actual immediate. So we'll have sources is the same thing, but we're going to have new immediate. And the immediate here will be a value in the same type. So the value for the immediate here, we will just say we'll do value error strconv parse int. So we're going to parse an int from the original source file's lexeme of the integer literal. So we'll pass in a lexeme here. It's going to be base 10 and 64 bits. And the lexeme is going to be g.file.lexeme, and we'll pass in the node start and the node end. If there was an error, I suppose we'll use the errors already. We'll say error for this node could not parse ints, and then we'll pass in the actual error from the Go standard library. So once we've got our destinations and our sources, we can then emit another instruction into the block. So we'll say insta, and this is going to be op. This is going to be a const because we're going to load a constant into a register. The destinations is destinations, and the sources is sources. So I think maybe we'll try this out and see if I've missed anything. We'll go over to main, and we'll just do it directly in here. So we'll call this ir.fin. We'll say function main returns S32, and we'll just return 1, 2, 3. So we need to call types.newChecker.check. I'm not going to check for the errors right now. We'll pass in the node and the file. Then we need an ir.new generator. This is going to give us a module and maybe some errors, which I suppose I will check. I'll just print them out. I'll just print error, and then I'll print the module. Maybe I'll print a new line between them. So the generator is going to work on the node and the file again. Seems to think I want Go types all of the time, so let's change that to my ones. It's changed it back. Types. There we go. Test. Okay, I didn't mean to run test, but this is just as good. So type has no field or method string. Okay. Type. Yeah, that's right, it doesn't. So we'll do func t type string, return string. So this is going to be, oh, I seem to be, okay. I did the stringer in the wrong place. Okay, so the stringer goes in here. New type is basically going to look up. It's basically going to convert based on this thing still. So we'll basically have a look at the type. If it's basic, oh no, yeah, this is correct. So this is new type is correct, but the stringification of this also. Okay, yeah, I need to just create a type names table basically. String. Let's just take these. And then the stringer can just return type names t. What else is broken here? Cannot use string in split. Okay, so that's in IR. That is line 104. So I need to call that. Undefined AST module. Is this? Does it think I want Go AST? Yeah, and token. We'll do AST and token. I really wish the auto formatter wouldn't just assume Go all the time. But okay, line 148. No method, no field or method name on function decal. Oh, that's right. Yeah. Okay. So let's go to here. This is actually node idents.name. Next is undefined params and returns. That's true. So we'll have params. Params is going to be a bunch of values, but we don't actually parse parameters yet, so we'll leave that how it is. Returns is going to be a bunch of types. So we'll take the function type, which will be the types.node type for the function decal node. This will have the returns on it. So we'll just do a for over ret range type.returns. So these are, if I go to the function.go, these returns are already a types.type, which means that I can just append here, because returns in the IR is just a slice of IR types instead. So we're just going to convert. So we'll append the conversion, which is new type, of the types.type. Okay, so type.returns. Okay, I need to typeset this to a types.function, which should be safe to do at this point. We shouldn't be calling this without having a type checked AST. So g.block is undefined. That is true. G.block should be lowercase. Anything else? Missing return on line 212. Okay, yeah, so the int actually needs to return the destination, because we want to use the virtual registers in other places. Return statement can return nil. We don't need anything from that. Okay, so now we've got an assignment mismatch in main. Okay, so parser now returns errors. So we'll say if the error does not equal nil, film.println error os.exit1. Let's do the check here as well. If this is not nil, then we'll do the same thing. And then I suppose I may as well do it properly here. New generator seems to. Oh yes, okay. These should be passed into generates. Okay, now let's do go run dot. and we get nothing. But there were no errors. So let's have a look at IR. And we'll just see at the end of this, we do functions. Okay, so I need to actually append the functions. So g.fns equals append g.fns with a function. Okay, so now we get function main. No parameters, no returns. So I need to actually print the returns here. But we're storing the const 123 into a virtual register 1 with the type S32, and then we're returning the value from v1. So that looks correct. We'll need to go to the function stringification here and actually print out the returns. So we'll do strings.join returns with comma space, or just a space maybe. No, we'll do comma space. So we'll do var returns is going to be a bunch of strings, and then for ret range over f.returns returns append returns rets.string. So now we see that we're returning a single S32. So let's go back to main and we'll change this to return multiple values instead. So let's do, so if I do 456 and try and run it, this should give me a type error. Expected 1 return, found 2. So if we put 2 returns in here, now 123 goes into virtual register 1, 456 goes into virtual register 2, and then we return both of them at the end here. So let's just implement, for example, we'll do 1 plus 2 minus 3 multiplied by 4 divided by 5. This is going to crash at the moment. CLS, go run. Okay, so this is crashing because I'm not handling AST binary in the IR generation. So let's just add binary here. So we'll need the LHS, which will be the g.generate of node.lhs. We need the RHS, which will be the RHS. Then the return of this will be the destinations. So destinations is going to be some new register which we put the value into, and the type of this is going to be new type, and we're going to look up the node type for the binary node. So this is going to take this type in here, and before we get the destinations, we're already generating this. So we're already generating the sources. So LHS and RHS are basically the sources here. So we'll also do g.block.emit, and we'll emit an instruction for some kind of operation. So this will be add mul, add sub mul or div. The sources is going to be the concatenation of LHS and RHS, and the destinations is just the single destination register that we've got. Oh yes, so now we need to define op. So if we switch on node.op, so in the case that we see that it was a token plus, op will equal add. In the case of minus, we'll have sub. Asterisk will be mul, and slash will be div. And then we need to actually define op. So op will be an op kind here. Okay, so let's have a look at this. So we've got 1, 2, 3, which is the first return. That's v1 here. And v1 is being returned directly at the bottom here. So that's fine. Then we had 1 plus 2 minus 3 multiplied by 4. So the 3 multiplied by 4 should be done first. So we've got 3 and 4 here in 5 and 6. So we're doing a mul with 5 and 6 and putting that into v7. v7 should be divided by v8, which was 5. So we've got v8 here. Into v9 is the div of v7 and v8. So that seems fine. We've got the add 1 plus 2 minus the 3 multiplied by 4. So we've got the plus is being done as its own operation here, which is correct. So that v2 and v3 go into v4. And the v4 should be sub the value of the next expression, which is v9. So the v9 is here, v4 is here, and then v10 becomes the sub of v4 and v9, and then we return v10. So this is correct. We're generating the correct intermediate representation here. So I think I'll leave it there. Maybe I'll have a check over and see if I've missed anything here, but if I haven't, then I may be able to start generating some machine code for this.